Welcome to this explainer. Today, we are breaking down the exact blueprint for training a flawless custom AI voice model, and we're going to do it without getting completely lost in the technical weeds. If you've ever tried to train a text-to-speech model and ended up with something that sounds like, well, a metallic underwater robot having a panic attack, you are in the exact right place. We're going to unpack the absolute fundamentals of hardware, model architecture, and training data so that absolutely anyone can understand what's actually happening under the hood.
Okay, let's dive right into this, because there's a core truth we really need to establish immediately. Final quality is a chain of ceilings, and you inevitably get the lowest one. Your final voice model can never, ever exceed its weakest link. Think about it. You could have absolutely perfect data, but if your architecture is limited, your audio is going to be limited. You can train for 1,000 hours on a massive GPU, but if your data is noisy, your audio will be noisy. Final quality is just a chain of ceilings. Data, architecture, training, inference, and you are always capped by the lowest one. So to conquer all these concepts, here's our perfectly structured roadmap for this explainer. We're going to cover sound fundamentals, the two jobs of TTS, the architecture ceiling, data quality and consistency, training and discriminators, and then we'll wrap up with shortcuts to perfect audio.
Let's kick things off with Section 1, Sound Fundamentals. Before we can teach a computer to speak, we have to understand what digital sound actually is to a machine.
Fundamentally, sound is just air pressure changing over time. A microphone measures that pressure and literally just writes down a number. If we're using a standard 24,000 Hz sample rate, just 4 seconds of audio equals exactly 96,000 individual numbers. And this introduces what we call the scale problem. I mean, if we ask a neural network to directly output 96,000 correct values in a row, where a mistake in just one of them creates an audible, annoying click, well, that's incredibly difficult. This single, massive number shapes the entire design of every single text-to-speech system in existence.
Because predicting waveforms directly is so insanely hard, we use a spectrogram instead. We slide this little window across the audio to measure the frequencies, map them to 80 mel bands, which perfectly mimic how our human ears kind of squash detailed high frequencies together. And finally, we completely discard the phase, which is the timing alignment of the waves. This is a brilliant trick that squashes a 4-second clip down from 96,000 numbers to just about 30,000 perceptual numbers. But, and this is a massive catch, discarding that phase information makes recreating the original audio very, very difficult. Moving into Section 2, the two jobs of TTS. This internal division of labor exists inside pretty much every modern text-to-speech architecture.
Whatever your specific architecture happens to be called, it always has two distinct jobs. Job 1 is the acoustic model. Think of this as the director. It converts text to sounds and decides on the rhythm, the pitch, the emphasis. Job 2 is the vocoder, or the audio engineer. It takes that compact spectrogram from earlier, invents the missing phase, and upsamples it into a real, listenable waveform. And you can actually use this to diagnose your own model. If it mispronounces words or has weird pauses, that's a Job 1 problem. Go look at your data. But if it sounds robotic, metallic, or gritty, that is absolutely a Job 2 problem, pointing directly at your vocoder.
All right, Section 3, the architecture ceiling. Now that we actually know what the vocoder does, let's talk about how default library settings can seriously ruin your model's potential.
Let me share a real cautionary tale here. A development team literally lost an entire day of training compute just because they left their architecture settings on default. They were accidentally using a low-quality preset. We're talking a tiny 1.66 million parameter vocoder that uses these really aggressive upsampling jumps. To get smooth, rich, natural audio, you need the high-quality preset. That one uses 14.34 million parameters and 4 gentle upsampling steps. Wider networks with smaller, gentler steps always produce vastly smoother audio simply because they don't have to invent too much detail all at once. Now, I want to slow down for a second because this specific mathematical rule is absolutely crucial. We call it the hard link. Your upsample rates multiplied together must exactly equal your hop length. And the hop length is just the chunk of audio data the model processes at one time. So if you're using upsample stages of 8, 8, 2, and 2, those multiply to exactly 256. If your hop length is also 256, you're golden. The vocoder gets one frame every 256 samples and outputs every sample flawlessly. But if these numbers disagree, your audio will come out at the completely wrong speed, or your model might just refuse to build altogether. Which brings us to Section 4, data quality and consistency. It is totally time to debunk the myth that just dumping hundreds of hours of random audio into a folder equals a great model.
Let's set some realistic expectations for dataset sizes. If you only have 1 to 3 hours of audio, that is strictly for fine-tuning an existing voice. Period. If you try to build a brand new model from scratch with that, it's going to sound incredibly rough. To build a viable single-speaker model from the ground up, you really need 10 to 20 hours. And if you want to hit that real comfort zone, producing top-tier, classic reference quality, you should be aiming for about 20 to 30 hours of audio.
But please remember this: consistency absolutely dominates quantity. 5 perfectly consistent hours from one microphone in one single room with one speaking style will easily beat 20 messy, inconsistent hours. Average speech just sounds muffled and lifeless. You also need perfect text normalization. If your transcript says the digits 1995, but the person in the audio actually says 1995, you're teaching the model pure nonsense. Spell out your numbers. And finally, keep your clips short. Models generalize really poorly beyond what they train on, so keeping your training clips under 6.25 seconds guarantees tight, predictable quality.
On to Section 5, Training and Discriminators. Let's look at how the model actually learns what sounds real under the hood.
Here's a wild hardware reality. Generating full-length audio for every single training example wouldn't just take forever, it would literally melt your hardware. So to keep memory usage manageable on modern GPUs, which are often using that efficient BF16 precision, the vocoder is only given a random tiny slice of each clip. It only sees 8,192 samples at a time. That is a mere 0.34 seconds of audio. Your vocoder is literally learning how to speak by looking at third-of-a-second fragments, piecing together local textures without ever needing the context of the whole sentence.
Now, what's really interesting here is how we force the model to sound human. We use adversarial training with discriminators that basically act like judges. The MPD discriminator folds the waveform to catch errors in pitch and repeating structures. But the MRD discriminator examines spectrograms to catch metallic, buzzy, and grainy artifacts. The developers in our source material actually left MRD turned off by accident, and they suffered with buzzy audio. If you ever hear a specific buzzy noise in your outputs, you simply need to turn on the MRD discriminator, whose entire job is to hunt down and eliminate that exact artifact.
Finally, Section 6, Shortcuts to Perfect Audio. I want to leave you with some actionable, massive time-saving techniques you absolutely have to use before hitting that train button.
The absolute biggest shortcut in all of text-to-speech training is warm starting. Training from pure scratch means your model starts as totally random noise and literally has to figure out what human speech even is first. Don't do that. A full fine-tune loads an entire existing model, which is incredibly fast if the language matches. But hey, even if your language or phonemes differ, you should still use a vocoder warm start. This copies only the waveform generation weights. Because the physics of sound are universal, a vocoder trained on English audio can perfectly generate Spanish waveforms. This one tip alone will save you tens of hours of compute time.
Okay, here is your rapid-fire, empowering pre-flight checklist. Verify your real sample rates. Check your exact text normalization. Validate the hard link maths so your hop length matches your upsample rates. Enable both your MRD and MPD discriminators. But most crucially, when you hit train, read the printed parameter count that pops up at startup. That number is the actual fingerprint of the architecture you built. Don't just trust your config file, trust the printed parameter count. If it says 1.66 million instead of 14 million, stop the training immediately.
Remember, silence from your terminal is not success. Always verify what you've built. But right now, you have the complete blueprint. You understand the sound fundamentals, the vocoder architecture, the data consistency rules, and the hardware shortcuts. The ceilings have been lifted, so the only question left for you is, what voice will you build? Thank you so much for joining me in this explainer. It's been a blast, and I cannot wait to hear what you all create.